A lot of what I'm going to talk about comes from more of a research setting. So before Trifacta, I was a grad student at Stanford in the visualization group there. And a lot of what I'll present today is actually, it's related to what we're up to at Trifacta, but a lot of it is actually research that's been kind of continued at the visualization group. In particular, we're talking about kind of data profiling and how we can apply techniques from perception of large-scale visualizations to visual data profiling. So just to kind of set some context on what I mean by profiling, I think it's useful to kind of look more generally at the analysis process. So this is kind of a 5-stage characterization, not meant to be authoritative, but just kind of set a little bit of context. So if you think about kind of how analysis is typically done, there's usually maybe a first stage where you acquire your data, either from some relational database, maybe a text file or spreadsheet off the web, wherever you have to kind of get the data you need. And the second stage, actually what we focus a lot on at Trifacta, and again, I won't talk about too much today, is kind of wrangling or transforming that data. So how do we integrate it? How do we structure it? Maybe it's things like parsing data out of log files or restructuring spreadsheets, all of the work that goes into just kind of cleaning and preparing data for analysis. The third stage I call kind of profiling. This is really understanding your data, and that's mostly what I'm going to talk about today. What is inside my data? How is it distributed? Are there data quality issues? How does it relate to other data I might have? Really kind of this high-level understanding of just what's inside of your data. The fourth stage, probably traditionally what most people think about when they think about analysis or data science, is this idea of kind of modeling, things like predictions and forecasts. And then finally, the last stage is kind of just sharing this out, either in some type of static report or maybe some dynamic report with the rest of your team. Now, of course, this is a highly iterative process. You might get to the end and have to go back and acquire new data. Maybe as you're profiling, you find some data quality issue that forces you to transform your data in some way in the wrangling phase. So you're kind of tight in this loop during a good analysis process. Now, what's interesting is if you kind of look at this process generally and where visualization's been used, it's actually mostly been focused on the last phase. You kind of get done with your analysis, then you want to report out to your team. You build some static visualization, and kind of over the last few years with tools like Tableau, these reports have become more dynamic, but still typically it's not really in the exploratory phases of building the model and analysis. It's mostly in the sharing out. So what I've been interested in kind of in a research setting for the last 6 or 7 years is really how do we take visualization and statistics and kind of push that up the pipeline so that throughout the process you can leverage these tools. Because interestingly, if you talk to analysts and data scientists, most of their time is actually not in the modeling or the reporting phase. It's actually in the first 3 phases of just kind of getting to know their data and working with it before they get to the modeling phase. So I've been working on this problem for a while. At Trifacta, we work a lot on these first 3 phases, but today I'm going to focus on kind of one specific one just due to time constraints and talk about profiling. So again, when I think about profiling, it's really this idea of what's inside of my data. So there's kind of 2 different ways I kind of think about this. The first one is you get kind of a new data set. What's inside of it? Is it useful? Are there things you really need to be aware of to make sure that you can kind of trust your analysis process? So this is things like how was it collected? How is it distributed? Or is there any bias in that data set that you really need to be aware of? Similarly, I think kind of throughout the process of working with data, lots of times you're transforming it, you're maybe aggregating it, joining it with other data sets, filtering out certain rows that you don't care about. All of these things really have significant impact on how much you can trust the results of your analysis. So it's really important to kind of, throughout this process, to make sure you're constantly testing any assumptions that you make. So I think this quote kind of sums it up nicely. This came from an interview study that we did a few years ago that's in VAST from a data scientist at a social networking company. And she said, "It's easy to just think you know what you're doing and not look at data at every intermediate step. Analysis might have 30 steps. It's tempting to just do this, then that, and then this, but you have no ideas in which ways you're wrong and what data is wrong." I think this is really important because really throughout the analysis process, you do lots of things to your data. Again, whether it's filtering it, aggregating it, computing new features. And every time you do that, you might be introducing some bias. You might not quite understand what's actually the effect of what you're doing to your data. And it's very important to kind of test those assumptions as you go so that you can kind of trust the results downstream. And our approach really is to try to use visualization and statistics to kind of help with this process of data profiling. And one of the reasons why I think really is kind of summed up in this quote is that this comes from Martin Wattenberg. Says, "The first sign that a visualization is good is that it shows you a problem in your data. Every successful visualization that I've been involved with has had this stage where you realize, oh my God, this data is not what I thought it would be. So already you've discovered something." So I'm going to talk a little bit about how kind of different visualizations and the choice of visualization you use can really have a big impact on how you kind of perceive kind of overall features in your data, and in particular data quality issues that might affect your analysis. So I'm going to start with kind of a very simple example. I'm sure many of you have seen a chart like this, just a line chart. In particular, this is census data from 1850 through 2000. So this is the count of farm laborers in the US. And what happened was in 1890, there was a big fire. All the records from the census got lost. And in this chart, which actually a lot of tools do today, whenever there's missing data, they just plot it as a 0. So kind of misleading, but at least it kind of calls it out as something kind of odd. So if you're, if you're going to kind of dive into the details, you'd probably eventually realize something was wrong there. A lot of charts kind of take this a step further, and instead of plotting it as 0, do kind of a simple linear interpolation through the values. The chart looks less funny, but in some sense this is even worse, right? It's kind of concealing the error in kind of a more fundamental way. Perhaps kind of a better solution is to leave a gap there, so some white space. And actually this works pretty well depending on your time range, but you can imagine as the scale gets smaller and smaller, that white space becomes harder to perceive. So perhaps a better solution, and it's probably not going to show up that well on this screen, but kind of even speaks to the point even more, is kind of using some annotation there to call out the fact that something's missing. So there's kind of a gray line there. So this is kind of a simple example with a very simple chart, but you can already see how, with simple visualizations, these kind of choices really affect, your perception of data quality issues. This is kind of a more fun example, maybe a little more nuanced. So it was great talk on graphs a few minutes ago. This is a social network, actually of Facebook data. In fact, this is my PhD advisor and co-founder's Facebook data. So every node in this graph is one of his friends that he retrieved from the Facebook API, and then there's a connection between nodes if his friends are friends with each other. So in this graph, it's kind of cool. You can see kind of clusters that emerge from his different networks. I think one of these is his undergrad, and the other one is kind of more professional, and so on. But really, in this view, you don't really get a sense, is there anything wrong with this data set? You can take the same data and plot this in a matrix. And here what you have is kind of along the left axis, you can think of this as kind of each of his friends. Along the top axis, each of the friends. And then there's a point filled in with color if they're friends with each other. And again, you start seeing some of the clusters. And in particular, this was sorted so that those clusters would appear kind of more prominently. That's kind of a standard technique with these matrix visualizations. Instead, if we do something much simpler, and instead of sorting it so that the clusters appear, we just sort it by ID. So everyone has a unique Facebook ID. We'll just sort the left axis by ID and the top axis by ID. And what we notice now is that there's this kind of huge gap in the bottom right. So again, this would be kind of startling. Why would that be just empty? So it turns out, actually, I don't know if you've used the Facebook API, but the time this was collected, I think about 2 years ago, they used to limit the number of results you would get back from the API to, I think, 5,000 results. So this is a huge gap that's not actually an artifact in the data itself, but just merely about how it was collected. So again, you can start seeing these kind of like nuanced ways in how you present the data can really affect your perception. So for us, what we started thinking about is, okay, if we want to build a profiling tool, what types of stuff would we really want to kind of support as high-level tasks? The first is really helping people understand the shape and structure of their data, and the second is to find and, to the extent possible, fix any data quality issues that might be in there. So with that, I want to kind of jump into kind of a live demo of a tool. With this, just kind of demonstrate an example profiling scenario. After this, I'll kind of get into some of the design considerations that went into building such a system. So for this example, I'm going to be looking at FEC data. So this is individual contributions to political campaigns, so how much money people are donating to various campaigns. And one of the kind of goals of this process is going to be to help people, again, understand what kind of data do they have. So I'm going to jump into some of the profiling features here to kind of dive into some of the features. So when we kind of pop open the profiling view, what we kind of see along the bottom left, or the kind of the far left column, is what we call kind of a column browser. And the idea is just to give you a high-level summary of all the distributions of your data. So based on the data types, we'll give you a certain type of visualization. So for instance, here's report type. It's a string variable. We'll kind of bucket it up. You can see things like Q1, Q2, Q3, and so on, and get an overall distribution of those values. Similarly, kind of scrolling down, you see a number of other attributes and their distributions. Now, you can imagine with kind of data sets with lots of columns, this exploration become tedious. So what we'd like to do is kind of layer in additional ways to explore the data based on different attributes of the data. So for instance, we might be able to kind of just sort all of these columns. Might do something simple like column type, so you get a sense of what types of data are available to you. Up here at the top, we see transaction date, followed by a number of numerics. Looks like there's some geography, and then a number of text columns. And then what we can do is kind of dive in to individual columns to get kind of a richer summary of that attribute. So diving into transaction date, again, we see it's a date time. We see the title of the column. And then over here on the left, we start giving you some metrics around data quality. How many values are errors? How many values are missing, extreme, and so on. In this case, it actually looks fairly clean, which is a good thing. But we might want to dive into more of the patterns in the underlying data. So one thing we do in this tool kind of down below is based on variations in the data that we see, we'll try to recommend visualizations that kind of highlight those variations. So for instance, with the date column, you can imagine binning this in probably 15 different ways: by day, by quarter, by hour, by year, by month, and so on. And a lot of analytic tools give you kind of that flexibility. What's important here is that based on kind of properties of the data, we can start recommending visualizations that will point out some of these variations and then leave out visualizations that might not show anything of interest depending on your task. So for instance, here we can see kind of in the month-by-month histogram, you start seeing some relationships here that are kind of interesting, like the end of each quarter, there seems to be a little bit of spike in the amount of donations to political campaigns. Similarly, during day of week, it seems that people are more likely to donate during the week than on the weekends, and more people seem to donate at the end of the month instead of at the beginning of the month. So these types of relationships start popping out. They're kind of interesting in the context of one variable. But perhaps more interesting is when you start looking at these in the context of other columns. So for instance, if you were kind of interested in the end of the month, you could select these days and see not only kind of the subset across other visualizations in this attribute, but also start exploring them along the left here and the relationships to the other attributes. Now again, searching through all these columns can be kind of time-consuming and tedious, so can we kind of rely on the system to start finding interesting relationships based on the data that I've now indicated is interesting to me? So again, kind of navigating in the column browser here, we can say, let's sort for related columns, find columns that are somehow related to both transaction date and potentially the selection we've made. And what we see here is that report type has kind of gotten promoted near the top. If you don't know the data that well, it might be kind of surprising. Why is report type correlated or related somehow to day of week? When you start diving into the data, it becomes pretty obvious. Again, I think I showed this earlier. Report type is things like quarter one. When we select that, we see it's obviously very related to the transaction date. Quarter two, again, very related. Similarly for year end. So I guess what's important there is not only kind of noticing certain patterns in the data, but then being able to place those in context so you can kind of understand how does it relate to the rest of my data. Similarly, just to show a couple other examples very quickly, we might be interested in values that have errors, so we can look at mismatched values. Looks like transaction type has a bunch. The state people are donating from looks like it might have some. Again, when we dive into here, you start kind of getting a breakdown. You see things like, there's 5 missing values. The popular states kind of have more transactions, which makes sense, so nothing too surprising there. And then you see things like invalid values. Someone might have put ZZ here maybe because it was missing, maybe it was some type of crazy typo. So you can kind of choose what you might want to do with this. Again, I'm not going to talk too much about transformation here, but clearly if you see an invalid value here, there's things like deleting it, maybe setting it to null, and so on. Similarly, for things like state, you might want to plot it on a map so you can get a sense of, again, how does it relate back to other attributes. Just to show one more example, we can also look at things like extreme values, so not things that are kind of hard errors, but things that look like they're just kind of outside the normal distribution. We see subcommittee ID kind of appears to have some extreme values. It looks like there's just kind of 3 clusters here, though, so maybe not too alarming. If we go down to transaction amount, the amount people are actually donating to the campaigns, that might be more interesting. Again, dive into this part of, or dive into transaction amount. If we kind of expand down here, we do see that the frequent values, there's things like a few $100s, people donate maybe $1,000 to a campaign. And then kind of in the far right, we start seeing some of the extreme values. So probably some wealthy individuals donating kind of tens or $75,000. that might actually not be too surprising. Maybe more surprising actually is that if you look at the minimum value, it's negative. And if we dive into the histogram here, and in particular kind of zoom in a little bit close to 0, we do see again, a lot of density around 0, not too surprising. But then we see kind of to the far left here, a lot of negative values. So again, we might want to dive in and say, well, are these negative values kind of data entry errors, or are they actually kind of semantically correct? The only really way to do that is to look at either the raw values or kind of place them in context. So let's try to place them in context. Let's select the values we care about. Again, we could start sorting through all these columns. Instead, we can kind of play the same trick from before, look at kind of related columns, and we see here that memo text kind of appears as highly related, or at least more related than others. We can change the scale to make it a little easier to spot the kind of outliers here. And as you kind of map over these values, you'll start seeing a lot of things like refund of contributions, kind of indicating that it's not really a data quality error or some type of error in the data. It's in fact real data. The money's being transferred out of the campaign. So that was kind of a quick demo, just kind of showcasing some of how you can use both kind of statistics and visualization, and when you couple those together, you can really kind of make this process much more rapid of finding potential data quality issues and assessing them. All right. So I went through that system pretty quickly, and there's at least kind of 3 things that would be really fun to talk about today that I think kind of go into it. The first being, how do we kind of automatically choose which visualizations to show? I'm not really going to talk about that. The second is, how do we, as the data volumes scale, so that data set I believe is maybe a few 100,000 or a few million records. How do we make this scale to data sets that have millions and billions of records? And that's actually what I'm spending most of the time on today. How do we kind of build visualizations that support that and don't break down with lots of records? And then the third time is, how do we support real-time interaction over those data sets? Again, I won't have time to talk about the day, but after the talk, if you're interested, I'd love to chat more. Oops. Let me jump ahead here. All right, so we're going to talk about perception and not view recommendation. So again, the question is, how do we really visualize and interact with billion-plus record databases in real time? Again, I'm not going to talk about the interaction piece, so this will mostly focus on visualization and how do we make these visualizations perceptually effective. And kind of the trick that we play is really that whatever visualization we use, it should be limited by the chosen resolution of the visualized data and not the number of records, because clearly if we go by number of records, it'll break down at some scale. So just to make this a little bit more concrete, let's look at an example. Everyone's probably familiar with scatter plots. Pretty traditional visualization. Here I'm showing just a few thousand data points, and this kind of always happens with scatter plots at a certain scale. It suffers from overplotting. You can play a couple different tricks here, like jittering and alpha blending, and that'll kind of give you maybe another order of magnitude, but eventually it kind of always breaks down. So one thing you might try is kind of sampling the data, maybe doing stratified sampling or random sampling or some other technique. And this might work well. Unfortunately, a lot of times you might throw out kind of interesting substructures. You might throw out outliers or anomalies that are actually really interesting. Kind of a third technique is to kind of take the density and maybe just plot the model of the distribution. Of course, here then you're making kind of really tight assumptions about the underlying distribution of your data, which may not be valid. And then finally, the approach we kind of advocate is to use some type of binning scheme. So the idea here is you kind of break your data into discrete ranges, count the number of points or some other aggregate function within that range, and then plot that either using color or some other mechanism. So this is really nice because you don't need to throw away data in some sense. I mean, you are kind of making it more lossy, but you usually won't lose things like outliers in this approach. And you also don't need to make the same kind of tight assumptions that you might make with modeling. And as I'll talk about in a second, though, kind of the problem here, or the challenge is, how do you choose the right bins, the right number of bins, the right shape of bins, and so on. So again, let's use another example here of a data set. This is data from Brightkite. So it's a social network where people kind of go in and check in. And we took kind of 4 million check-ins from that network. And if you plot it on Google Fusion tables, at least as of about a year or two ago, they would use kind of stratified sampling to put this on the map. And what happens here is you kind of start seeing some patterns like people tend to check in around major cities, but then you start losing a lot of the detail. So instead, what we can do is use the binning technique from before and plot this on a map, kind of at a per pixel or roughly a few pixel area here. And what you see here is a lot more detail. So you get kind of the same effect as before, where you see lots of stuff in popular cities. But additionally, all the outliers from, say, Mexico and Canada that were not in the original chart are now apparent. You also start seeing kind of cool patterns like along interstate highways. There's these kind of streams of check-ins. And then there's kind of this fun one down the Gulf of Mexico, which turned out to be actually an account that was set up, I think, to track Hurricane Katrina in 2008. So that type of stuff starts emerging when you don't kind of throw away any of the data. So more generally, is there kind of an approach that we can take to kind of apply this across a lot of different sets of visualizations? And in fact, I think this one actually kind of works well. So kind of a 4-stage process here. First, you bend the data. So again, I talked about this earlier, but it's really just dividing the data domain into some buckets. For categories, it's in some sense already discrete. Though, if you've worked with high cardinality data, that can actually be a really big challenge. So there's some interesting things you can try there. For numbers, you can choose the binning intervals, uniform, quantiles, and so on. For time, again, you get into how do you choose the time unit, hour, day, month, quarters, et cetera. And then for geo, you can kind of bin XY coordinates after you do some type of projection to it. Now, when you kind of get into number of bins, or questions around binning, kind of the first obvious one was, well, how many bins? In some sense, more bins can be better because you get kind of a more detail. But a lot of times it might be too much detail, and you'll kind of always run into some type of pixel limit. So a lot of times this is where you want interaction, where you can kind of zoom and pan and that type of thing. But I won't talk about that too much today. Probably kind of a more subtle thing is kind of the shape of the bins. So a lot of statisticians have actually advocated using hexagonal bins. Most tools actually use rectangular bins instead. So hexagonal bins have been shown actually that people can estimate density better. You get less artifacts from the kind of the hard cutoffs and the rectangles. But most people use rectangles. It's a little bit, maps a little nicer to kind of query engines and query processing and just kind of the way people think about ranges. So I think typically most tools do that. So kind of moving on to aggregation, a number of different aggregate functions. I'm mostly going to talk about counts today, but really any aggregate function you could plug into this technique. Smoothing. This is kind of an optional step. A lot of tools don't do this. Actually, if you want more detail, Hadley Wickham has a great paper on this and how you can embed it in a framework actually similar to this one in 2013. But the main idea is you can kind of smooth out the data and kind of get rid of some artifacts. Makes it a little easier to kind of spot overall trends. And then the fourth step is kind of to then plot the data. So for plotting, the real question is, well, what visual encoding are you going to use once you have the data that you need? And really kind of what we're going to do is just simply choose the most effective visual encodings. There's been a lot of work on this, probably most famously from Cleveland and McGill, and I think it was actually 1984. They did a number of perceptual studies looking at how do people estimate magnitudes and kind of relative magnitudes using different types of visualization. So looking at things like how do people look at length? Can they estimate length better than area, better than slopes, and so on? So for instance, as an example, all of us looking at these bars, I don't know, you can kind of roughly guess that the smaller bar is maybe 1/3 the size of the larger bar. Then if you kind of take this over to circles, this is actually the same relative ratios. The big one's about 3 times bigger than the small one, but it's a little bit harder for us to kind of make that assessment. So more generally, if you kind of just look at all the different ways that people are kind of perceive data, and you kind of look at the estimation errors, you get this nice kind of relative ordering with position at the top and things like area at the bottom. And again, these are based on both kind of empirical estimates, doing the study of having people compare objects of different sizes, and also they have some nice kind of theoretical arguments for why this happens. And kind of more recently, kind of near the bottom there, things like volume and color have been used in visualization as well. And you see those actually kind of rank even lower on the scale. So, for instance, when I showed the map earlier, you might have noticed that we used big kind of circles instead of a chloropleth map, which is what most people are probably used to. Again, this goes back to the idea that area is actually much easier to kind of estimate than color. Plus, you get a lot of weird artifacts with the map because the states are all different sizes. So, kind of applying this to our use case here. For one-dimensional data, which a lot of kind of the overview and visual summaries that we use for kind of profiling to get a sense of distributions, we want to use kind of position or length encoding. So this is things like histograms and line charts, et cetera. For 2D, so really the choices get limited a little bit because you're already using both spatial dimensions to just encode the actual data values itself, or the x and y axis. So we actually need to kind of choose between area and color. So in the previous slide, I said, well, we should use area instead of color because area is better, which is true for certain cases. But color is kind of nice when you have lots of bins because you can apply it at a per pixel level, an advantage you don't really get with area because you're going to use up more of the screen real estate. And also with color, you get this nice kind of overall effect when you're just kind of perceiving patterns more generally. So let's focus in a little bit on color, again, using some examples. This is a bin scatter plot. And kind of the standard thing most tools will do is they'll kind of take a color ramp. They'll start at 0 to indicate, they'll start at white to indicate 0, and then they'll ramp up to some color such as blue. And kind of the darker the blue, kind of the higher the value. The problem with this approach, of course, is that for counts near 0, you kind of map so closely to the white that you can't even see the value. So outliers and other kind of interesting points are just kind of completely missed. So one little trick here is just to do some little discontinuity so that all those values become perceptible. So you can see on the right, it's a little hard to see on this screen still, but at least you kind of see more of the underlying structure and the outliers. Again, maybe a little bit more subtle than that is how do you actually interpolate the values from 0 to 1 or some minimum to 1. So most people, again, will use some type of linear interpolation, linear alpha interpolation. Unfortunately, actually, this does not map linearly to how we perceive the values. So instead, what a lot of studies have shown is using some type of cubic root to do the interpolation, then maps much more nicely to how we kind of perceive the linearity. So if we kind of just put this all together into a nice little formula for kind of doing the color encoding, we're going to kind of map to some luminance in between 0 and 1. We're going to look at the data value, x. We want to keep the small non-values visible so we can introduce this kind of non-zero intensity or kind of a minimum. In practice, I think 0.15 seems to work pretty well. Then we want to match the color ramp to perceptual distances. So that's where the scaling factor comes in of roughly about 1/3. And then if you want to kind of enable exploration across value ranges, again, I'm not talking about interaction, but things like zooming in and out, you're going to have some user adjustable min-max that you can kind of use for normalization. So if you kind of put all this together, you get this nice kind of design space of all the bin plots for both 1D data and 2-dimensional data. So again, back to the 3 challenges. I didn't really kind of go through all these. There's also kind of both effects and kind of how do you recommend visualizations, and then how do you make these things really scalable. I'm not going to talk too much about the interaction here, but one kind of interesting paper that came out actually this year was looking at kind of introducing latency into visual analytics systems. And what they found was if you introduce delays kind of around 500 milliseconds for certain types of tasks, not all tasks, you get kind of huge effects on people's ability to kind of explore their data, and it really affects kind of qualitatively that exploration. So it is really important to keep the kind of real-time interaction and that latency down to a minimum. With that, I do want to acknowledge a few other people. A lot of the stuff I discussed was actually research done by others from my old research group, including Jeff, Leo, and BA. So if you're interested in more details, they might even be better to ask than me. And with that, I'd like to open the floor for any questions.
In your tool, the profiling was more of an exploratory exercise rather than and the focus was looking at outliers or invalid values and things like that. But what if I'm looking to see what the tool can provide me and kind of do some profiling on the relations based on the column values and say come up with suggestions that what these seems to be some. So after like removing all the outliers or the null values and things like that, this is the profile of the data. It seems these two dimensions are very much related or things like that.
Yep.
Do you do things like that, or are you like, is there something that you should do in the early stages of that whole 5-stage we talked about?
Yeah, so I guess there's a question, is there looking not just at one dimension, but multiple dimensions at a time?
Right, and also like doing correlation between them, like are they related or not? And things like that.
Yeah, sure. So I didn't show it in the demo. Actually, in the tool there is, I kind of clicked on the 1D profile. There's also two-dimensional stuff as well, where we do look at those types of patterns. In some sense, the brushing and linking is two-dimensional because you're starting to look at relationships across variables through exploration, but we also do offer visualizations that are aimed kind of more directly at 2 dimensions and which attributes are kind of interesting to look at together in the tool.
Okay. But this would be more, so if I want to like really look at the data, it will be more of a manual approach where I try different things out with the tool.
So yeah, I probably won't dive into a demo here, but the idea is when you select kind of an attribute of interest, we can then show you all the other variables that are kind of more related to that and might have more interesting patterns or associations based on, the types of properties you're looking at. Yeah.
You mentioned the cubic root was perceptually. Is it on now? There it is. Okay, you mentioned the cubic root was perceptually analyzed. I was just wondering what the citation was for that, because I've looked at pixel binning for quadratic root and logarithmic root based on data profiles that made a lot of sense. It was arguably justifiable because the data profile was either quadratic or logarithmic.
Yep.
I was just wondering what the citation was for the why cubic.
I don't remember the exact paper, but I think it's something to do with mapping to kind of the lab color space, LAB, so I'll get back to you on that. I just don't remember the exact paper.
Check. Okay. Is there any inherent, risk of overfitting, perhaps, like if you, develop a predictive model based on these visualizations?
Yeah, so absolutely. So I think our kind of general approach to all of these tools is, we try to couple both kind of the domain expertise with the statistics and machine learning and all the models that are running underneath. So all of the visualizations are kind of interactive. You can always kind of override them and look at some other visualization or explore the data. So we kind of think of it more as kind of suggested visualizations. And of course, sometimes what we suggest is the wrong thing. Sometimes it's the right thing. But we don't want to be kind of lock you into that one view. So as much as possible, kind of layer on exploration and interactivity on tops of the stuff we're recommending.
It seems like there's a human tendency to focus on outliers and edge cases. There's a tendency also to ignore them because there truly are outliers. How do you deal with that focus on the outlier, taking away from the focus on the core of the data?
Sure. So I think you're right, and I think it almost actually kind of goes back to the last question in some sense too. How you deal with outliers is really context dependent, depending on your analysis task. Right? And sometimes the outlier is the only thing you care about, and sometimes you don't care about them at all. So again, one of the things I didn't really show there is we'll point out outliers, but then the question is, well, what do you do with them? Do you delete them? Do you just keep those? Do you want to annotate them so you don't get rid of them, but at least people downstream are aware that they exist? So again, we try to leave that decision in some sense in the hands of the domain expert or the analyst, but as much as possible, kind of just point these out and help you kind of discover them and make that process more efficient without kind of telling you what you should do with those outliers or how much you should care about them.
So the sampling activity, is it on the left to the domain expert or the tool be able to do that?
Do what, sorry?
So you talked about sampling of data to better aid visualization of the profile of the data. Is it something that tool can do it, or is it something that domain expert would have to do it?
Yeah, sure. We offer sampling in the tool for certain types of transformations to keep the interactivity up. And yeah, we offer a variety of different sampling techniques that you can do within the tool.
All right. Any takers? Any more questions? If not, I think thank you very much, Sean.